Hi, everybody. This will be probably a short stream today. I have other priorities the coming week, and it will also be a recorded one because I want to be present to look through the comments when it goes live later today. And this stream is a little bit dedicated to Wolfie and his latest video in which she showed us some long-range photographs and how much of the objects visible on this were hidden, and used the wonderful Earth curvature calculator from Walter Bislin's to calculate how much the amount of things hidden is. And I'm sure Wolfie can do this in mental arithmetic too. But to those who can't, I want to show an easy way how you can go and achieve very good and very close results to Walter Bislin's calculator with a few relatively easy operations in mental arithmetic. And I switch to my document camera, and it is not completely adjusted like it should be. I think that's better so far. Yeah, okay. Now, let's draw a horizontal line or level line, or doesn't really matter, and 3 plumb lines, which aren't actually what I say here. These are simply lines which I will label here on top, and the first one I label with divide by 2. The next one I will label with take square root, and the next one I again label with divide by 2. Okay, looks very I have a nice camera picture here. I can switch and this, so you can look at me a little bit and see how I do the drawings. Okay, now this looks a little bit magic so far, and here is another mystery box. And now we go. And what we basically have to do, and I take Wolfie's example here of the 2-meter high camera and 20 kilometer distant targets. We have, I'll put as a reminder, I put it here that we have to use centimeters, but I can put a meter column here. And we had a viewer height of 2 meters. And this is obviously 200 centimeter. And what we do now is we divide it by 2. And we take the square root, it's obviously 10. And we divide this another time by 2. By 2 gives us 5. This mystery box here will be explained later. And we have a 20 kilometer viewing distance. We subtract the 5 from the 20, leaving 15. We then undo these operations. We have divided here, we've divided, square root divided, and so on. We undo this now, so we multiply this 15 by 2, gives 30. Then reverse of square root is square. We multiply this. This is in kilometer, of course. Metric units, guys, metric units are much better than imperial ones. Yeah, and now we have to square this. That gives us 900. And this step division by 2 also undone is doubling, is 1800 centimeters. And now comes the beauty of metric units. If I want to do the centimeter to meter, I have just to move this here by the decimal point by 2, and I come to a hidden height of 18 meters. And if you use Walter Bislin's advanced Earth curvature calculator, then you will see that result is quite close. How close I will show you with a comparison spreadsheet a little bit later. And I also could do now this other example, but of course I preferred the one which has the easy to take and square root, and I want to have a nice sheet of paper here, not so many things crossed out or so, and therefore I will look. What I actually could do, I could do these steps in a calculator once more. The other example from Wolfie was he had a 10-meter viewing height, which would be 1,000 centimeter. I do it in mental arithmetic. Divided by 2 will be 500. Now, the square root of 500 is a little bit difficult, but here we can do the trick that we can ignore the 100 and add 10 to the result, because the square root of 100 is 10. And so we only need to take the square root of 5. And if, as we know, 2 squared is 4 and 3 squared is 9, so we are probably very close to the 2. And my gut feeling is that we have here the square root of 5 is about 2.2. So one shift for these 2 shifts of the order here, 1 shift here. So we get about 22. And what is 22 squared? This is 400 plus 484, I think, not quite 500. So we have to add a little bit more, say, let's put a 3 here. Maybe it's a 22.2 or 22.3. We again divide this by 2, leaving us with 11, say 2 here. We only do an estimate. So now we subtract the 20, so we get 8.8 here. And again, in reverse, 16, 17 point. In Germany, we have a comma as decimal separator, but in English, I say point. You have 17.6. Now we have to square this. Squaring 17 may also be a little bit difficult here. We can apply the same trick basically as we did in reverse, as we did with the zeros here. If I move the 0 point to the left, I come to 1.7, and I know that 1.73 is the square root of 3. So squaring the 17 will approximately give us 300, I think. I guess we don't only do a rough estimate. And again, by 2 is 600. And so we should have 6 meters of hidden here. And I have prepared a spreadsheet in which I compare the results of this rough estimate. And we come also to this box here. I can now label it. This is the box in which we can either improve our estimate if we add 1% here. 1% is easy to add, as it's just if I see this number, 1% is of 5 would be 5.05 and so. But the more important use of this box, and even easier, is 10% here. If we add 10% to this number, and of course, when we have subtracted it from the total distance, it was also 20 here. If we have subtracted it from the total distance, we have to reverse this step and add, we have to add 10% and subtract 10% here. Okay. Now, here again, I have put the calculation steps, and we get for the Wolfie's example, with the 2 meter viewer's height and the 20 meter target distance, we get 18 meters. Here, this is the 10 meters viewer height, which I did seconds. We get 6 meter 22. I had, with my rough calculation, I came to 16 meter. And the other one is exactly 18, because all the numbers so nicely fitted here. And I can again, of course, put my own image here. Okay, now what are the results? How exact are the results? You see here we are relatively. I have some more examples here. We stay most often within 5%. Here it gets a little bit worse, but if you look at the numbers, we have a 32-meter result and are 3 meter off. I think in practice, you will never know actual refraction that well that this really is relevant. But this calculation we did so far was for the no refraction, was the infamous geometrical horizon distance. And if you want a little bit better results, you can do 1% here in this adjustment factor in practice. And I have also the option here to change this adjustment to 10%. And now I click here for refraction, and you see we are not only well in the ballpark up to really large distances. This is a viewing distance of 100 kilometer, which you probably in many practical situations have. We are very much in the ballpark, and except doing square roots, which requires a little bit training, and squaring, both can be done using approximately the same guessing and interpolation techniques. If you know the squares of the number 1 to 10, and you can interpolate a little bit, and if you know, for example, that if you square and your interpolation, for example, has to go 10% up. So you want to square 2, this gives you 4, and 2.2 where 10% more. And if you square, you get about double that difference in the result, and vice versa. And I like to do this kind of rough estimates in mental arithmetic. Maybe the background is that I grew up in times where electronic calculators weren't ubiquitous. They didn't even exist in a sense. When I went to school, our school was one of the first who had a programmable mathematical calculator about the size of a large electrical typewriter. That was in the 1970s. And before we used slide rules, and those who still can use a slide rule know that you always have to keep track of the order of magnitude of the result in your head, because the slide rule helps you, for example, with this exercise here, calculating the square root. This would be easy, but you would have to know the order of magnitude, because the slide rule tells you only the digits, but not where you have to put the decimal point. That you have to know by yourself. Okay, finally, for the math geeks among you, so I think we have already lost all flat earthers since long. And I hope it's sufficient if I give credit here verbally to this iMath EQ program. Here is what is behind this calculation. You can see here going these 8 centimeter per kilometer, which is nearly as exact as 8 inch per mile squared. And the division by 8 is split in two here. One division is under the square root and the other is outside the square root. So this is effectively the division by 8 we need. This here is the factor we have to change if we want to improve the accuracy, or if we want to incorporate standard refraction. And then from here we go back, again applying this factor, and now first subtracting the result. This is calculating here the tangential point from the observer side. We subtract this from the total distance, so we have the remaining distance, and we do here the the correction. If we want to put it in, if we only do a rough estimate, we assume Z is 0, so this multiplication doesn't take place. We multiply by 2, square the whole thing, multiply another time by 2, which is effectively then a multiplication by 8. And this is my suggestion I would give to all who are on the road with your P900 or whatever, and you have approximate numbers of what you take photographs of. And if you want to roughly estimate or even calculate in case you have no online access to Walter Bislin's wonderful calculator, you can do it with mental arithmetics, or for example, with a pocket calculator which has no sine or cosine but gives you at least the square root. And then this is also a nice way to do it. Here we have it. Now let's do this second example here. If assume we have no trigonometric functions on our calculator, we start with a 10-meter viewing height. Let's first delete this. So 10-meter viewing height is 1,000 centimeter. And we divide by 2 at first, giving us 500. We take the square root. Well, not bad, my 22.3, rather 22.4, okay. We divide by 2 once more. We do 10% correction upward now, which is a multiplication with 1.1. Okay, this now is the number we have to subtract from the object distance. So I make it negative and add 20. I could have also subtracted 20 and then inverted the sign. So this is the remaining distance. Now we have to the 10% correction, we have to put it into the other direction. So we multiply this again with 0.9. We double it. We square it. Is the result, and double it again. And this gives the result in centimeter. I'll just revert this, 3.84 meters. Now I'm really curious what Walter Bislin's calculator result was. Here we go with my. Okay, this was, we have to enlarge it. So this was the 10 meter, 20 meter, 3.84 meters. Obviously, refraction here changes a lot. It changes the result of the amount hidden. Yeah, refraction changes a lot. But we are very close here, within 2% of the result from Walter Bislin. These numbers here in this column are copied from Walter Bislin's calculator. Okay, that was it for today. This is only recorded now. Maybe I try to stream it at a point in time where Wolfie has at least a chance to look at it if he wants to, and I can sit there and be in the live stream. Okay, so bye.